to look at Dalton's law of partial pressures. So what this does is it takes the ideal gas law from just a single gas to how we apply it in terms of a mixture of gases. And it turns out to be quite easy. Dalton's law of partial pressure says that the total pressure exerted by a mixture of gases in a container at constant V and T is equal to the sum of the pressures of each individual gas in the container. So that the P total is the sum of the pressures due to just the components. Another way to think about this is if it's an ideal gas, the other molecules in the ideal gas don't notice each other. So you calculate the pressure due to one, then calculate the pressure due to the next, because it was just that in the volume, add them together, you got the total pressure. So essentially the ideal gas molecules don't notice each other, and that is why the pressure, the total pressure is just the sum of the individual partial pressures, the pressure due to just one of those components. So some of the notation here, so the mole fraction, usually written as X or sometimes a Greek psi, Greek X psi, we'll see both of those, is the moles of the component divided by the total moles of the mixture. So the sum of the mole fractions is going to be 1, because if you add up the mole fractions of each component, that gives you the total moles of the mixture. So it's you'll see it notated as Ni over N total. But because of Dalton's laws of partial pressure, another way to write this is the mole fraction is the partial pressure of one component divided by the total pressure. These are all equivalent due to Dalton's laws of partial pressure. This is an ideal gas law. So for real gases, there can be slight deviations, but in dilute conditions, relatively low pressure conditions, not freezing temperatures, then this is a very good approximation. Okay, so let's just do a direct application of this. A gas mixture is composed of 13.9 grams hydrogen gas, 64.8 grams nitrogen gas, and 78.7 grams ammonia. What's the partial pressure of each gas and the total pressure of the mixture if it's kept in a 25-liter sealed vessel at 150 degrees C? Okay, so the first thing we'd have to do is convert from number of grams, which ideal gas law doesn't really care about, to the number of moles. So we have 13.9 grams of H, 2.02 gram of H2 to be precise, H2 molecular mole H2. The grams of H2s cancel, and we get 6.88 moles of hydrogen gas, 64.8 grams of nitrogen gas, 1 mole of nitrogen gas divided by 28.02 grams of N2 gives us 2.31 moles of N2 and 78.7 grams of ammonia. Ammonia 17.03 grams of ammonia per 1 mole of ammonia. And so that is 4.62 moles of NH3. Okay, so that gives us a total of 13.81 moles of gas. So now we can calculate the total pressure because we know the total number of moles. It doesn't matter what they are. It just matters that there's moles of ideal gas. So P tot, the total pressure, equals nRT over V, just from rearranging PV equals nRT. 13.81 moles, 0.08206 liter atmospheres, mole Kelvin. And what's this? 150 degrees, we have to add 150 degrees C, we have to add 273. 273 plus 150 gives 423 Kelvin. So 423 Kelvin divided by 25.0 liters. Moles cancel, liters cancel, Kelvin cancels. We're left with a pressure. We get 19.2 atmospheres, so fairly high pressure. So now, in order to get PI, we're going to multiply by the mole fraction. So the mole fraction of hydrogen is going to be 6.88 divided by 13.81. These are both units mole. Those cancel, and we get 0.498. You notice that there's the least hydrogen gas of any of the components in the mixture, but in terms of mole fraction, hydrogen is essentially half the gas. So mole fraction of N2 is 2.31 divided by 13.81 equals 0.167. And the mole fraction of ammonia is 4.62 divided by 13.81 equals 0.335. And if you check this, if you add them up to significant digits, it'll be equal to 1. So we now, what do we want? We want the total pressure, or the partial pressure of H2, the total pressure due to the hydrogen, which is just going to be this pressure multiplied by that mole fraction, and that gives us, I'm writing it as P tot times PH2 equals P tot times chi H2, which is 9.56 atmospheres. Partial pressure of N2 is equal to P tot mole fraction of N2 equals 3.21 atmospheres. And the partial pressure of NH3, P tot by mole fraction NH3 is equal to 6.43. And if we add those up, you plug it into a calculator, you'll see it does indeed add up to that corner. Oh, hello. There we go. If we add it all up, you'll see it does in this case. Yeah, it adds up to exactly 19.20 if you plug that into your calculator. The total, the partial pressure is, the sum of the partial pressures is the total pressure. Now, there's another way we could do it, in which you could take each of the individual moles of gases and calculate the partial pressure using PV equals nRT, except instead of 13.81 moles, for calculating the partial pressure of hydrogen, you'd put in 6.88 moles. And what you get out is the exact same result. You get 9.56 atmospheres for H2, 3.21 for nitrogen gas, and 6.43 atmospheres for ammonia. And so either way you do it is fine, because the partial pressure for an ideal gas, you can calculate the individual components separately, because they ignore each other, and then just superimpose all the three systems together. The total pressure will be just the sum of the pressures from each of those.